This is a short lecture on how to set up the equations for projectiles. Since you're always free to choose your coordinate system, always choose it to try to simplify your problem. And I always try to keep certain rules in mind. That saves me from a lot of sign errors. For one thing, I put the XY plane on the ground level, on the surface of wherever you are, surface of the Earth, surface of Mars, doesn't matter. I put that XY plane as ground level, then Z is always the height above the ground. Some people like to put the XY plane up in some, I don't know, and then, at any rate, this is what I do, and I do it consistently, and that saved me a lot of sign errors. So you will have a launch height, and then you can just call that Z naught. Then let the x-axis be the direction of the launch of the projectile. Okay, and I'll show you what that, how that looks in the next slide. So here is a picture of a cannon that would launch the projectile. Right. Now, what I said is always put the XY plane down here on the ground. So this is going to be your XY plane. You might quibble and say you should put it down at sea level, but oh well, you might do that too, and that could be okay. Now here's the next thing to do to simplify your problem. You see the direction that the cannon's pointing in, put that as your x-axis. So there's your x-axis right there. And now your z-axis, of course, is vertical. To go right here. And the y-axis will be off into the paper like that. So there's your y-axis. There's your J. This is your x or your I-axis, and this is your k-axis. I'll show you how that simplifies things in a minute. Now your launch height right here, that's your launch height, and it's Z naught. Now you need the angle that you shoot this cannon off at, so you can just figure out the angle from parallel to that ground, parallel to your x-axis, and this was not a very good drawing. At least I didn't do a very good drawing. The picture's fine. Let me just do a solid line here. Okay, then your angle is going to be this angle right in here, and I'll call it theta. So theta is the angle of elevation of the cannon, or however you're shooting the projectile. If you don't like cannons, think of bows and arrows or something else. Now this is the most general equation for the path of the projectile, and I can show you as that by choosing the coordinate system or putting the coordinate system the way I did, you will eliminate a lot of terms. Okay, first of all, the x naught, y naught, z naught is the launch, the initial position of the projectile. So that's, as you can see that from the equation. If I set t equal to 0, then all the terms involving t are going to go, and the t squared terms will be 0, so I'll just end up with x naught in the I direction, plus y naught in the j direction, plus z naught in the k direction. Because we put the origin of the x-axis at the place where the projectile is launched, then this is 0, this is 0, and all you have is the z naught term, which is your launch height. So we've eliminated this one, and we've eliminated this. So with this Vx, Vy, and Vz, that has to do with the initial velocity at which the projectile was launched. So it have an x component, a y component, and a z component. But because we lined up the x-axis, try to draw a little picture here, we lined up the x-axis with the direction in which the cannon is shot. This is the theta here. Then there's no z component because we only have a projection down into the x. So you have this is Vx right here, and Vx would be the magnitude of that velocity times the cosine of theta, just project it down, and then there's going to be a y-directed component to the velocity. You can write it here or over here. So z-directed component of the velocity, and that's the magnitude of v times the sine of theta. But by lining up the x-axis, you know you don't have this y component, so that's 0 as well. Now Wx, Wy, Wz is the wind, and you have to compute that. I have written only here for a steady wind, although it can be blowing in any direction, but it's steady. You have a more difficult problem if you include a non-steady wind. You also have a more difficult problem if you include air resistance, but that was in I'm not doing that here. I'm not doing the full problem. Okay, now let's look at acceleration. Well, because I put x and y right on the surface of the Earth, there's this term is gone, this term is gone, and az is simply minus g, it's acceleration due to gravity. So when you go to solve these problems, you can just plug into the equation. You don't have to write this most general equation. You can write it in a more simplified form. If something is 0 initially, don't even bother putting it in there, of course. Then you're looking for the peak of the the highest point for the projectile goes, and you're also looking for the time it comes back to the Earth. And so remember what you're looking for there. If you take the derivative of r, right, you're getting velocity, but where the velocity is 0, the projectile is turning around. Right here the velocity would be 0, so it's a critical point, and you can use some reasoning to determine if it's a maximum or a minimum. It's going to be a maximum in these cases. And then to find the point that it returns to 0, just set r equal to 0 and solve. Of course, you'll find you may have an initial point over here or a negative value, and you can disregard that. Also, you can use a computer, and I'll show you some computer results now. In the following examples, the initial velocity was 1800 feet per second, and it was the projectile was launched at a 60-degree angle, so put theta equal pi over 3 because I like to work in radians. Be careful when you work in degrees. And it was launched from a height of 12 feet. There's be 3 curves on this next graph. The red one was no wind. The green one, there was a wind blowing in the minus y direction, 0.5, and this, watch your units, feet per second. That's not a very strong wind. And in the blue, you have the blue curve will have both an x, y, and a z components to the wind, and you can see the effect now. So this is the result with no wind. You can see these are all launched from 12, although it's hard to see the scale over here. Now the green one had a wind blowing in the minus y direction, and it blows this projectile off course, so it's kind of hard to see here. I was using something called graphing program for 3D, and I wasn't real fond of it, but it was good. Okay, so here's the one where the y at a minus 0.5 in the I direction, in the j direction. And now, in this case, the wind had both x, y, and z components to it, and the z component was in the positive z direction, so you see the wind contributed and blew the projectile up to a higher height, but it also blew it off the initial course when there was no wind. So like I say, you're welcome to do this on the computer as well after you write out the equations. So write out the equations, take some derivatives, but then you can plot them too. Unfortunately, I was going to say you could plot it with dplot, but you can't really plot it with dplot. So to see what you can do, try to make some sketches. You probably can't put them all on the same graph.